Quantum computing is a rapidly advancing field of research and development with the potential to revolutionize the way we approach a wide range of problems in science, engineering, and beyond. While there are still many challenges to overcome in realizing the full potential of quantum computing, the future of this technology is looking bright. It will influence many industries including finance, healthcare, and cybersecurity. As such, there is a growing demand for professionals with expertise in quantum computing. Google, IBM, Microsoft, AWS are few of the big players that are already in the quantum computing market. Companies like Volkswagen, JP Morgan Chase, Airbus, CERN, Biogen are either already using or testing quantum computing to solve business problems like simulating traffic patterns and optimizing traffic signals in real time, optimizing aircraft designs, financial services like portfolio optimization, risk analysis, and fraud detection, simulating the behavior of subatomic particles for improving drug discovery process. These are just few of the quantum computing use cases out of the many underway. Whether you are a student, a computer scientist, a data scientist, a mathematician, a physicist, or a business professional, if you like to stay at the forefront of technological innovation and be prepared for the next wave of computing, you must consider learning quantum computing. I will discuss physics concepts first in an intuitive manner, avoiding formulas, derivations, technical jargon as much as possible. Thereafter, we will take a look at classical computing to understand where we are with classical computing, what are the challenges, what does the future look like. We then jump into quantum computing, understanding the need, the implementation, the application, the challenges, and the future work. Quantum computing will be discussed in section 3. However, before I begin with the section 1, that is the physics prerequisites, it's important that you understand the selective list of topics that you see here have been carefully chosen to enable you to understand the quantum hardware implementation when I go through section 3 without feeling overwhelmed with physics. Quantum computers use atoms, ions, electrons, photons to store data, and quantum storage and computation takes advantage of quantum behaviors. Electromagnetic radiation is used to control and manipulate these quantum particles in the quantum hardware, and many types of quantum hardware need ultra-cold temperatures. Let's start with the first topic then, atoms. The idea of building blocks making up all matter was proposed thousands of years ago by a Greek philosopher. He said that if you keep dividing any material into smaller and smaller pieces, you would obtain the smallest piece possible that still contains all the properties of the material, like the texture, taste, color, etc. His ideas were rejected back then though. Fast forward to early 1800s, scientists investigated this idea for years and had good reasons to accept that matter is indeed composed of elements, where each particular element is made up of single type of atoms, and different elements combine to form variety of compounds. The periodic table consists of the arranged list of elements discovered thus far, arranged according to their properties. The periodic table also has few synthetically created elements. The yellow highlighted portion here is a category of elements which are called metals. Metals are characterized by properties like you can create thin wires or hammer them into thin sheets without breaking the material. They reflect light and shine, and they possess a special property that makes them good electrical and thermal conductors, which we are going to discuss in a while. Further scientific investigations reveal that atom itself contains many smaller particles, and these subatomic particles have a role to play in how the atom behaves chemically and physically. Thus began the era of quantum physics, the study of subatomic particles, in the late 1800s. In the standard model of an atom, we have 17 subatomic particles as shown in the image. The protons and neutrons that reside inside the nucleus are made up of quarks. The nucleus occupies a small and dense space as compared to the entire atom. As shown in the image, if the nucleus were 10 cm across, then the atom would be 10 km across. There is huge empty space. Another analogy would be if the atom were a huge cricket or football stadium, then the nucleus would be like an apple in the stadium. The subatomic particles, we'll call them quantum particles, have been studied extensively and are active areas of research. Two important properties of these particles are charge and mass. A particle with charge exerts a force on other particles that have charge. Likewise, a particle with mass exerts a force on other particles with mass. Yes, which means we are exerting a force on everything around us that has mass, including Earth. The force exerted by particles with charge can be attractive or repulsive, whereas the force exerted by particles with mass is always attractive. The key point to note is these particles are able to exert a force from a distance. Imagine Magneto, Wanda, or Doctor Strange lifting objects without being in physical contact with these objects. Scientists have strong evidence to believe that there are force carrier particles that are actually exchanged when one particle exerts a force on another. These particles that constitute matter transfer discrete amounts of energy by exchanging these force carrier particles with each other. The word quanta means discrete packet of energy. You cannot have half or quarter packet of energy. You can only have integer multiples of these packets. That is why it's called discrete, not continuous. When two charged particles interact with one another by applying an attractive or repulsive force, they exchange the force carrier particles known as photons. Out of the four fundamental forces, strong nuclear force, weak nuclear force, gravity, electromagnetic force, that exist in each atom, photons are the carriers of electromagnetic force. I find these forces pretty magical. They hold the atom together. Otherwise, the protons would have moved away from each other due to repulsion, and electrons wouldn't be confined to the atom. The best explanation that we have for the origin of all these atoms and subatomic particles is the Big Bang theory. Each of these subatomic particles and atoms contain the energy from the Big Bang explosion that occurred about 13 billion years ago. All we do is transform this energy into various forms for our use. All kinds of energy can be broadly classified as kinetic energy and potential energy, where anything that is moving has kinetic energy and anything that exists in a force field and resisting that force must have some energy to be able to do so. We call that potential energy. This potential energy can be converted to kinetic energy, and note that potential energy is always due to a force. This means that the subatomic particles have both kinetic energy and potential energy. Electrons are in a constant, unpredictable motion in the large empty space inside the atom. All we have is a probability function predicting where the electrons are more likely to be found. These regions are called energy levels. Think of it as orbits of different shapes at varying distance from nucleus. The electron cannot be anywhere between any two energy levels. If it gains energy, it will jump off to higher energy level, and then when it falls back to its original energy level, it will emit the energy in the form of photon. The energy contained in this photon will be exactly equal to the difference in energy of the two levels. Note that these energy levels are different for each element. We are all aware of electricity. One of the types of quantum hardware utilizes an electrical circuit to replicate the behavior of an atom and uses that circuit to store information. Let's delve a little deeper into the concept of electricity, magnetism, and the subatomic particle that carries the electromagnetic force before we take a look at this circuit. As we just discussed, that electrons occupy energy levels in the atom. The outermost orbital is called the valence shell. In metals, these valence shell electrons have some degree of freedom and they can move from one atom to another. This makes them good electrical and thermal conductors. If you connect a metal wire to positive and negative terminals of a battery, then electrons will feel repulsion from the negative terminal and will start moving towards the positive terminal. This is electric current, and we utilize this energy from the moving electrons for all electrical appliances. Semiconductors, on the other hand, are elements that have mixed properties of both metals and non-metals. They are useful because their conductivity can be altered by inducing impurities into their crystal structure and few other ways like application of temperature or light. Silicon is the most commonly used semiconductor. Transistor, which is the key component of classical computers, is created using a semiconducting material. Before we get to understanding more about photons and where we encounter them in our macroscopic reality, let's understand the electromagnetic force in a little more detail. What is electrical force? It is just the attractive or repulsive force between charged bodies. As we discussed already, a charged body will exert a force on any other charged body in its force field. Force field is the region where the impact of the charge is felt. A moving charge exerts a similar force on other moving charges in its force field. This force by moving charges on moving charges is called the magnetic force. The electrical and magnetic force are related to each other. That is why we call it electromagnetic. To understand the relationship, let's visualize this setup, where current is flowing through a wire, which means electrons are moving in the direction shown, and a positive charge external to the wire is moving along with the electrons at the same velocity. These electrons are hopping from one atom to other, thus leaving behind atoms with less negative charge, basically positive ions. Note that ions is just a term that we use for charged atoms. By default, atoms are neutral, equal number of positive and negative charges, that is to say, equal number of protons and electrons. If electrons are added or removed from the atom becomes charged and we call it an ion. In the external positive charge frame of reference, the electrons are stationary and the positive charges in the wire are moving in the opposite direction. Thus, due to length contraction, the positive charges are a little closer to each other, in other words, have more density than negative charges. Hence, the external positive charge experiences a repulsive force. It is more intuitive if you visualize this from the frame of reference of being in a moving car and looking at the equidistant trees at the border of the road along your path. When you are moving, the distance between the trees is lesser compared to when you look at it from a stationary position. Essentially, it is special relativity in action. Moving charges can exert an electrical force on other moving charges, and we name this force magnetic force. The larger implication of this fact is that now, any charged particle that is in motion possesses this additional power, thus each electron inside the atom has a magnetic power. In addition to moving around in different energy levels, electrons behave as if they were spinning about its own axis, thus behaving like a tiny magnet, whose direction depends on the direction of the spin. The spin is quantized, meaning there are only two possible spin orientations. This simulation of Stern-Gerlach experiment by quantummadesimple.com shows evidence of quantization of spin. The fact that quantum particles can be in two states simultaneously is a key feature of quantum computers. An electron can be in superposition of spins. However, when you measure it, it will collapse to one of the two states. Quantum realm is full of such bizarre phenomena. We spoke about electrical circuits being used to store information in quantum computers. There also exists a modality of quantum computers wherein we generate single photons and store information using these photons using a setup that can detect and measure the properties of a photon. Now that we have the technical background, let's look at photons. What we perceive as light from sun is actually just a flow of oscillating photons. As the photons move, there is a variation in the electric force field. Variation in electric force field causes variation in magnetic force field, and this pattern continues and makes the photons travel through vacuum. The energy of each photon is related to their oscillation frequency, and the intensity of light that we receive is related to the number of photons we receive. Each photon can be viewed as a discrete packet of energy. Ever wondered why the sunlight is more intense in high altitude regions? And you can feel comfortable even at minus 5 degrees Celsius temperature. The atmosphere is thin at high altitudes. As you move closer to sea level, the atmosphere is more dense and more photons are absorbed by the atmosphere. We receive a spectrum of frequencies from the sun, and a portion of this range is visible to human eye in the form of white light, which can be further divided into frequency ranges that we perceive as different colors. If you have had the opportunity to witness the magnificent northern or southern lights that can be viewed in geographical regions around the magnetic poles of Earth, here is the technical reason behind this spectacular phenomenon. We receive a lot of charged particles from sun. These particles are deflected towards the poles of Earth by our planet's magnetic field and interact with our atmosphere. The colorful sky that we witness is just a result of the atoms and molecules going through excitation and then emitting photons. Some of the dominant colors seen in the aurora are red, a hue produced by the nitrogen molecules, and green, which is produced by oxygen molecules. We use a slightly modified version of the circuit we are about to discuss in one of the types of quantum hardware to create an artificial atom, which is used to store data, and the atom is controlled using microwave pulses. We will just discuss these two electrical components as this is crucial to understanding the quantum hardware modality. Capacitors and inductors are electrical components that are engineered in a manner that makes them capable of storing energy as electric field or magnetic field. Capacitor is just two conductors separated by an insulating material. It stores energy in the form of electrical charges. To charge a capacitor, you just need to connect it to a battery. The electrons flow through the connecting wire to one of the metal plates, and because of the insulating layer between the metal plates, the electrons are not able to flow to the other plate and just get deposited on this plate. The electrons on the other plate feel repulsion and thus start flowing away from the plate, leaving behind a positively charged plate. If you were to connect a charged capacitor like a battery to a circuit, current would flow until the capacitor is completely discharged. From our discussion so far, you would have some idea of the relation between electric and magnetic fields. There are multiple laws describing how they affect each other. For example, if a wire carries current, there is magnetic field around it due to the moving charges. And if you place this current carrying wire into an external magnetic field, the two magnetic fields combine to produce a force on the conductor. A changing magnetic field can induce current in a conductor. Few of these laws form the working principle of an inductor. An inductor stores energy in a magnetic field when electric current flows through it. When it is connected to a circuit, when the circuit is switched on while the current is increasing to gradually attain its maximum value, the changing current induces changing magnetic field. Note that the geometry of the conductor, it being a coil, plays an important role here. The changing magnetic field creates a force such that it opposes the change in current. It starts acting like a resistance to the increasing current. In simple terms, view inductor as a device that does not like change in current, and it will always provide a force opposing the change in current. When the circuit is switched off and the current starts dropping to zero, There is again a change in magnetic field, and this time the inductor opposes the drop in current, thereby producing a force in the opposite direction. If you connect the inductor and capacitor in a circuit as shown, it behaves as an oscillator comparable to that of a pendulum swinging back and forth. As the current starts flowing due to the charges stored in the capacitor, energy starts getting stored in inductor. When the capacitor reaches zero, inductor reverses the direction of current and charge starts getting stored in the capacitor. If there was no loss of energy, the oscillations would continue forever. Note that a wave is nothing but a mathematical representation of a periodic variation. In this case, there is a variation of current or charge. In the case of sunlight, it is an electromagnetic wave. In the case of sound, it is variation of pressure that our ear converts to variation in current, perceived as sound by our brain. Quantum computers require ultra-cold environments. Let's understand why. The energy left over from the Big Bang keeps the whole universe warm. Temperature is just a measure of average kinetic energy of particles in any substance. Absolute zero is 0 Kelvin, which in Celsius is minus 273 degrees. Close to absolute zero, it is possible to manipulate and control quantum particles. Researchers found that ultra-cold molecules are relatively long-lived and stable. They resist reactive collisions with other molecules. In quantum computing, where we use photons, electrons, atoms, molecules to store information, it is important to be able to control and keep the particles stable and minimize the unintended interaction of the particle with neighboring particles or environment in general. Thus, we need to keep the hardware in ultra-cold temperatures. The average temperature of space is 2.74 Kelvin. For the quantum computers, we use dilution refrigerators that are capable of achieving temperatures in the range of few millikelvins, basically colder than space.